Alright folks, here's part 2. Sorry about the sound in the last one. I'm not really sure what went on. Hopefully this one isn't scratchy. But here we go. Here's how we would do a problem like this. We want to know a solution of potassium dichromate has a molarity of 0.145 molar. What's the concentration of potassium ion? And what's the dichromate ion's concentration? So first we need to write an equation. So we've got, let's see, potassium dichromate. That's a +1, that's a -2. So I crisscross it. There's my chart, or my formula for it. Get rid of these things. They were just there to help me figure out my formula. And we're saying this is a solution, so we're going to assume that it's aqueous, meaning it's soluble in water. And now this is going to dissociate into 2 potassium ions and 1 chromate ion. Dichromate, actually. That's Cr2O6. Or 7, I'm sorry. And Cr2O7. And that's going to -1 charge. So if my concentration of this was 0.145, my concentration of the dichromate anion is also going to be the same, because we've got, in my balanced equation, I've got a 1-to-1 ratio of these two. And then my concentration of my potassium ions are going to be twice that, so 0.29. Right, so this is going to be my potassium ions are going to be 2 times 0.145 molar, and then this is going to be 1 times 0.145 molar. So all just comes from our balanced, called ionic equation, or dissociation equation. So note about solubility, things that are soluble, meaning they dissolve in water, so things like sugar, things like salt. A lot of ionic compounds dissolve in water, are soluble, and then insoluble, things that don't dissolve. So if I take sand, mix it in with water, it's not going to be soluble. Sometimes we mix 2 solutions together, the ions can interact in such a way that a solid will form and will precipitate out. So a precipitation reaction is where a solid forms where 2 aqueous solutions had originally once been around. So here's one. Precipitates, they tend to be insoluble. So if I have a solution of nickel 2 chloride and sodium hydroxide, when they dissociate, the nickel ions and the chloride ions spread apart, and we add some sodium and hydroxide ions, the nickel is going to get together with the hydroxide anions, and they're going to make a solid precipitate. And that reaction looks like this. So we've got sodium hydroxide in the pipette, and we've got our nickel 2 chloride in our solution, this green solution, and these chunks are of nickel 2 hydroxide, as well as all of the junk at the bottom. So precipitation, you think of precipitation as if we think of rain falling from the sky. Well, the precipitate is falling out of solution. Way to figure out if this compound is soluble, well, we've got a table in our reference booklet. So those folks that run Disney will make sure we get you a copy when we see you in class tomorrow. It's on page 13. It's like a multiplication table. But in the meantime, some general guidelines is sap and CAN, compounds that contain sodium, ammonium, and or potassium ions all tend to be soluble. And then compounds that contain chlorates, acetates, and nitrates also tend to make compounds that are soluble. So we're going to use our solubility rules to figure out if the products for the following reactions are soluble or not. So these all look like double replacement reactions. So our copper is going to join up with our sulfate. And then our ammonium is going to form up with our nitrate. Our copper, according to this formula, is a +2. So we got a +2 over here. That's a -2, +1, -1. So we don't have to add in any coefficients to balance this out. We're good to go. It's balanced. Now to figure out if these are soluble, you can look them up in the table, or if we remember our sap and can, sodiums, ammonium, and potassiums. Here's ammonium, as well as chlorates, acetates, and nitrates all tend to be soluble. So here we've got ammonium and a nitrate, so it's like a double whammy. So if it's soluble, we're going to put AQ. We didn't mention anything about coppers or sulfates, but if we look at the table on page 13 of our reference guide, we're going to find on the left-hand column copper 2, and sulfate, we're going to find an S in there. And that also means it's soluble. So this sulfate is going to be soluble as well. So no precipitate is going to form. If we look at this, iron 3 chloride plus silver nitrate. Silver nitrate is the stuff that we used in our most recent lab. We're going to do a double replacement. So we've got silver chloride plus iron 3 nitrate. This was a +3, so we're going to crisscross our charges, get a 3 there. That's a +1. Silver's a +1, chloride's a -1, so that's good. Let's balance this. We're going to need to put a 3 out in the front of the AG, and then a 3 out for the AgCl. And that looks like that's going to be balanced. So, looking at our rules, silver chloride, that's neither sap nor can, so we have to look that up. Silver and chloride. You're going to get in our table a little I, meaning insoluble, which means it's going to form a solid. And then this is a nitrate, so that's most likely going to be soluble. But if we look it up, we double check. It's also going to be soluble. It's going to be soluble, so it's going to be aqueous. So if I mix iron 3 chloride and silver nitrate together, I should expect chunks of silver chloride to come raining down or precipitate down out of solution. All right, so we can boil that equation down into what we call a net ionic equation. This just shows the reaction between the ions in solution that are forming that solid product. So from the previous example, really the only thing that's happening is, well, these here are both aqueous, so they don't really the iron's not really with the chloride, and the silver's not really with the nitrate. Since they're dissolved and they're aqueous, we have iron 3 ions and chloride ions, and silver ions and nitrate ions. When a silver joins up with chloride, it's going to make our product, our precipitate. But we're also going to left over here, since this is aqueous, we're going to have iron ions and nitrate ions in solution as well. So we've got iron and nitrate ions in solution on both sides of our equation. So really, the iron and the nitrate aren't really doing anything, so we can ignore them for a net ionic equation. So net ionic equation, we've got to follow the following rules. Atoms must balance, charges must balance, and we only show the ions that are reacting or forming a precipitate. The others are just kind of along for the ride. So let's look at the precipitation of calcium carbonate, or limestone, from calcium chloride and sodium carbonate. So here's our formula equation, just like what we have seen in the last chapter. It's going to be a double replacement. We know one of the products is going to be calcium carbonate, and the other one's going to be sodium chloride. And we got our formulas. These are our correct formulas. We've got a +2 and 2 -1s, and a +1 and a -2. And since these are solutions, we assume that these are aqueous. But it says we've got a precipitation of calcium carbonate. So calcium carbonate is not going to be aqueous. It's going to be a solid. So we're going to make solid calcium carbonate. And then sodium chloride, we could look that up, but sodium chloride is familiar to us because it's table salt. And we know salt's dissolvable in water or soluble, so we can make that aqueous. Let's balance this. We're going to end up with 2 out in front of here, and that's about it. All right, so our ionic equation, essentially all we do is take any of the things that are aqueous and split them apart to their ions. So calcium chloride consists of aqueous solutions of calcium plus 2 chlorides. And then sodium carbonate, that's aqueous. We have 2 sodiums and a carbonate. They're going to split apart. And we're going to make calcium carbonate, and I'm running out of room here, sodium ions and chloride ions that are both aqueous. Oops, right happen there. Anyway, so we come back to this equation, and just like in math, if you got something on opposite sides of the equal signs, opposite side of the equation, they can cancel out. So if we look on here, we've got 2 chloride ions, and we've got 2 chloride ions in solution. We've got 2 sodium ions in solution, 2 sodium ions in solution. So we can ignore them when we write our net ionic equation. So our net ionic equation is just going to be calcium ions plus carbonate ions to make solid calcium carbonate. So that would be our net ionic equation, meaning these are really the only things that are reacting. If we notice from the above equation, the chlorides and the sodiums are unchanged on both sides of the reaction, so they're not really reacting. So the name for those things that aren't reacting, those are spectator ions. Just like at a soccer game or a football game, the spectators aren't a part of the action. They're just watching it happen. So let's write the net ionic equation, or all soluble for each of the following double replacement reactions. So this is going to be sodium nitrate plus copper 2 hydroxide. And we know that there's going to be 2, oops, jumping the gun here. We know there's going to be 2 hydroxides over here because the copper's got a +2 charge. We know sodiums and nitrates tend to be soluble. We can look it up and find that that's aqueous. And we can look up copper 2 hydroxide. And if we find that on page 13 of the reference booklet, copper 2 hydroxide is insoluble, meaning it's going to form a solid. So that's going to be the regular equation. If we balance this, we're going to need a 2 out in front of here and a 2 out in front of here. Now, since these are all aqueous, since these are solutions, we don't really care that they're together. We're just going to split them apart. But really the only things that we care about are what makes up our solid. So this copper 2 hydroxide is going to be made by precipitating out the copper 2 ions in solution with the hydroxide ions. Oops, I don't need those parentheses there. So that would be my net ionic equation. If we look at this next one, barium's going to be with sulfate. Barium's a +2, sulfate's a -2, so we know that that's our formula. And then we've got copper. This turns out to be copper 1 chloride. So we've got a -2. So we've got to have a total charge of +2. We're going to divide that by the 2, so that makes that a +1. That's why I know that that's copper 1. So if we balance this, we're going to put a 2 out in front of here, and that should take care of that. Now, sulfates, barium sulfate, we find that on our sheet. Barium sulfate we find is insoluble, meaning it makes a solid. And then copper 1 chloride. There's no copper 1 on our solubility table, so we'll just assume it behaves like copper 2. And we find that copper 2 chloride is indeed soluble. So that's going to be aqueous. And that was kind of counterintuitive. And we write S for something that's insoluble. So now all we care about are the ions that come together to make barium sulfate, which are barium ions and sulfate ions, AQ. And that's what we do for these net ionic equations. We'll pick up, well, we did an example like this previously, so we'll wrap it up here. So I'll post these. Obviously, I posted them if you're hearing this. So if you have any questions about this, shoot me an email or send me, or we'll set up a time to meet. Alrighty, good luck.